we will continue with our nonlinear dynamics course. So in this video we will discuss about van der Pol oscillator. The equation of motion for this oscillator is given by equation 17, where we have nonlinear term attached with the mu as a real parameter that indicates nonlinearity and damping. So in terms of the variable, this is a second order differential equation. So we will split that second order differential equation into two first order differential equations. So we introduce the variable x1 and x2. So x1 is x and x2 is dx by dt. So we may rewrite the equation 17 as two first order differential equations, which is given by equation 18. So now the fixed point is given by the right hand side of these two first order differential equation. At what values of x1 and x2 it becomes 0. So here naturally x2 is 0 gives the right hand side as 0, and here x1 as and x2 both of them as 0 gives the right hand side as 0. So the fixed point is given by x1 equal to 0 and x2 is equal to 0. Now we need to find out what is the nature of this fixed point. So for that we have to construct the linearize the first order differential equation and find the Jacobian matrix. This we have done in the last lecture, and that's the exact method. We just have to find the Jacobian matrix for this differential equation, and we find the Jacobian matrix as given in equation 19. So the eigenvalues of this Jacobian matrix decides the nature of the fixed point. So what we got as eigenvalues as given in equation 20. So lambda 1, lambda 2 are the two eigenvalues. Now the values of mu decides the nature of the fixed point, which we found as 0, 0. So let's take the cases. For case 1, let's take mu is less than minus 2. Then we get both the eigenvalues as less than 0 and they are different. So that this kind of eigenvalues denotes stable node. So the fixed point is a stable node. Let's take mu is equal to minus 2, then you will get lambda 1, lambda 2, both of them are equal as minus 1, which is less than 0. So the nature of the fixed point becomes stable star. So case 3, if mu is between minus 2 and 0, we'll have a complex value, and lambda 1, lambda 2 are complex conjugate of each other, and this kind of a fixed point, then this kind of the eigenvalues makes the fixed point as a stable spiral. So the mu is equal to 0 gives, it's just a imaginary value, it gives as a center, and the eigenvalue and the fixed point is called as just a center. So for mu greater than or less than 2, we'll have lambda 1, lambda 2 star, which has alpha is earlier it was negative, now it becomes positive, so therefore it is unstable. So mu less than 0 it becomes a stable fixed point, mu greater than 0 it becomes unstable fixed point. So let's take mu equal to 2, then we get unstable star. For mu greater than 2, we get unstable node. So these are the cases we get, and apart from this fixed point, for mu greater than 0, we can also find an isolated closed orbit in the two-dimensional spaces. So this kind of closed orbit is we call it as a limit cycle, and this limit cycle will be stable if every nearby trajectories approaches it. To find out all these characteristics, we need to solve the differential equation and see the trajectories in the phase plane. Then only we can understand all these characteristics of the fixed point. So for that, let's write a code in Python. So first import all the packages, necessary packages in the Python code, and then introduce the parameter mu and take all the possible values. Here I'm just taken one as an example. So next we'll define a function where we are defining the differential equation. This is the first differential equation where we have only x2. The second, we are just writing the right hand side, and this is the second differential equation, the two first order differential equations. So after defining the two first order differential equation, take the initial point where we start the solving the different initial condition. So we have this initial condition, and now use the time variable which is a derivative with respect to time. So let's take the time goes from 0 to 20, which made 1000 number of points between 0 and 20, and ODE int is the package which solves the differential equation. Now we just have to solve the differential equation, just writing this single line code. This solves the differential equation. So ODE int is a package. So we are defining, taking the defined differential equation, taking the initial condition and the time which we variable, and yes, we have written time as first, and sol gives the solution. So let's write the two solutions into, because we have x1 and x2 as the variable. So x1 and x2 we have separated in the two arrays, and now let's generate an animation for how it evolves from with respect to time. So for that, we'll set the x boundary, y limit and x limit for the graph, and we plot the fixed point. Fixed point is 0 comma 0, and this just the notation, and this is the animated plot. For each time interval we are making a animation. So we will, for each interval to take the plot, we have defined an update data function which makes the which takes the plot from each time frame, and it starts plotting. So animated set data, we have the solution, right? X1 and x2 data. We have the frame, it's a variable, and we'll give the frame as time. So then we, each time it will plot the graph, and this is the function we are defining. After that, we just have to use the package function animation. With that, we have the figure, and then the function update data, and each time the frames is the length of the time, and we give a name and save it. After all this, you will get an animation for each cases by choosing the values of mu. That we can, I have done that. I will show you each one case. Let's take the case 1. Here in the case of case 1, see here mu is equal to -3. It has started from some point, maybe 1 comma 0.5, and it is approaching towards the fixed point. That's why it is a stable fixed point, what we have found in the cases in from the eigenvalues. That's what is happening here, right? Let's take mu is equal to next, mu is equal to -2. -2 in this case, it is a stable star. So it goes from it moves towards the stable fixed point, right? From the eigenvalues only we can find the exact nature. So here it is approaching towards the point. So the next case is mu is between, yeah, mu is between -1. So in that case it is between 0, -2 to -1. It will be a stable spiral, right? So it makes a spiral kind of thing around the fixed point, and then it collapses towards the fixed point if alpha is negative. That's what we found, right? It's just moves and makes a spiral and goes to the fixed point. That's what we have seen in the from the eigenvalues. So the next case is mu is equal to 0. In that case, it's just a center. The eigenvalues are just imaginary. It just makes a circle around the fixed point. It is neither stable nor it's just a center. It makes a periodic orbit, whatever the initial point you choose. That's what it's just an imaginary value, eigenvalues. This is what we get for mu is equal to 0 with any initial point. Let's now let's take the case for mu. This is a very interesting point, because we have seen of if mu is greater than 0 it is unstable, but we have also said that we'll get a closed orbit. So let's see, do we get a closed orbit if we increase the value of mu is equal to 1 here. So we started from some 2 comma 3 or 4. So you can see it is moving towards the fixed point. It is unstable. Mu is greater than 1, it is unstable. It should not go towards the fixed point. Okay, it's an unstable fixed point now for this case. So you can see this, the curve is moving around the fixed point, but it is not collapsing and ending its path in towards the fixed point. It's just making a let's see if it makes a closed orbit. Yes, you can see that it is making a closed orbit, and this kind of isolated closed orbit we call it as limit cycle, right? Let's increase the let we have one more question, whether it is limit cycle is stable limit cycle or unstable limit cycle. So we have started with some away from the this closed orbit. Let's do it from very near to the inside the closed orbit. Let's have the initial point inside this closed orbit and see whether it goes back to it, or it shouldn't go towards the fixed point, because mu greater than 0 is always unstable. So let's see that. So here we have started from very near to the fixed point, and let's see what this is the initial point. Let's see what happens to it after some time. You can see that it is not going towards the fixed point, it's moving away from it. That's what it is, unstable. And yeah, it is making a closed orbit. It joined the closed orbit. Even if you start inside that closed orbit or away from the closed orbit, it finally comes back to that limit cycle. So therefore this limit cycle we can call it as a stable limit cycle. For any value of mu you will get the same structure. You can play around with the code by choosing different values of mu. Thank you.